All right, good morning, everyone. So, first thing, announcements. So, I'm going to have to move back my office hours by about 15 minutes today. So, it's going to be 12:45 to 1:45 instead of 1 to 2. Reason for that is I got to drive across town to pick up my daughter and bring her to her first ever dentist appointment. Awesomeness. So, yeah, basically I just got to go pick her up and bring her to the dentist. Hopefully, not too much bad news. So anyways, so that's about it for announcements. So today, we're going to start our last section of this class, which is thermodynamics. So this is where we're continuing for the next 3 weeks of this class, whatever is remaining. And yeah, so we're going to start off by talking about thermal physics. So this is the first section we're going to talk about. So thermal physics is just physics that involves temperature. So let's talk about what we mean by temperature. So when we talk about temperature, usually what we think of is we start off with two different systems. So say, for example, here's system number 2, which is going to be, for example, outside. And then system number 1, which I'm going to use a thermometer. So here's my thermometer. So this is system number 1. And let's say initially system number 1 is inside. And what I'm going to do is I'm going to test the temperature outside by bringing this thermometer outside. So all I'm going to do is I'm going to take this thermometer, I'm going to put it out here into the system of interest, which in this case will be outside, and I'm going to wait a little while. So what's going to happen? So initially, what happens is this thing is going to start off at one temperature. Let's call this thing T hot, because inside it's warmer than it is outside right now. So this is going to start off at temperature T hot, where outside starts off at a temperature of T cold. Then if I wait a little while, what ends up happening then is that the temperature on this one goes down, while this one technically goes slightly up. Until eventually what will happen then is that the temperature of this guy will match the temperature of this guy. So this will be approximately saying the same thing as T cold. And this is what we call temperature. So when we talk about temperature, sorry about that, Seth, what we really mean is the ability for two systems to be in thermal equilibrium. So when we originally talk about temperature, it's more of an operational definition of a statement that two things are simply in thermal equilibrium. So this happens by the process of heat exchange. So what ends up happening then is since this one starts off at a higher temperature than this guy, what ends up happening then is I get heat flow, which we call Q, and Q is equal to heat flow, which is a transfer of energy from a hot source to a cold source, which causes this one to have its temperature go down, this one's temperature goes up. We'll talk about what this one doesn't actually really change much, until eventually these two things reach, again, thermal equilibrium. So for us, at least for now, temperature is equal to an operational definition it simply tells me that two things are in thermal equilibrium. So two or more systems in thermal equilibrium. So for most of the time, when we talk about temperature, this is what we mean, is that two things are simultaneously at the same temperature. So it's an operational definition, meaning that they're in thermal equilibrium with each other. They have exactly the same temperature. Eventually, we'll talk about what temperature actually is in terms of regular thermodynamics, but for now, this thing is just simply an operational definition. So the reason for this comes from what's called the Zeroth Law of Thermodynamics. Zeroth Law. What the Zeroth Law of Thermodynamics says is, let's say I have 3 systems, system A, system B, and system C, where let's say this is system A, this is system C, and let's say system B attaches these two systems to each other. So this is system B. So what the Zeroth Law says is, well, if this one has a temperature of TA, this one has a temperature of TB, this one has a temperature of TC, then the Zeroth Law says, well, if system A is in thermal equilibrium with system B, simultaneously system B is in thermal equilibrium with system C, then system A must also be in thermal equilibrium with system C. So these two things imply that A must have exactly then the same temperature of C. So So this is what we call the Zeroth Law of Thermodynamics. So all this thing says is that, again, if A is in thermal equilibrium with B, but B is also in thermal equilibrium with C, then A and C must also be in thermal equilibrium with each other, which means that they have to have exactly the same temperature. Now, this may sound kind of like a stupid law, which I think the first time I heard it, I thought it was pretty stupid myself, but this is actually essential. And it's essential for the fact that if I wanted to measure things in thermal equilibrium, i.e. find its temperature, they have to then be at exactly the same temperature. What this thing is saying is then if I have these systems which are at exactly the same temperature, then I can reliably read the temperatures between these two things. If systems never actually came into thermal equilibrium with each other, I could never actually determine what was the system temperature like outside. If I brought my thermometer outside and I said, what was that temperature outside? Well, my thermometer never came into exactly the same temperature as what it was outside. I would never know what the temperature was outside. So even though it seems kind of like a stupid law, but it's an essential law, which means that, again, it's an operational definition that two or more things are actually in thermal equilibrium. So this is the point of the Zeroth Law. So the Zeroth Law just says that these things, when they read the same temperature, they actually are in thermal equilibrium with each other, which means that they are exactly at the same temperature as each other. So this is what we mean by temperature. So all temperature is, at least for now, again, is this operational definition which says that these two things are in thermal equilibrium. They have exactly the same temperature. We'll eventually talk about what temperature actually is. So good. So now that we know about that, let's talk about some temperature scales. So throughout history, we have come up with many, many different types of temperature scales. So how do we come up with temperature scales? So coming up with temperature scales is actually easier said than done. And the reason for that is because us as people, we don't measure temperature reliably. And what do I mean by that? What I mean by that is, let's say we're going from the summer into the winter. So we go from, say, 90 or 100 degrees down to 50 degrees. How do you feel at 50 degrees? From 90 or 100 degrees. You feel cold, right? Feels like you're standing inside a refrigerator. Now, fast forward a little bit. You go into the winter, where it gets down to, say, teens. Now you come out of the winter, going into spring, and you hit 50 degrees again. How do you feel now? Feel like you're getting ready to put on your bathing suit and go to the beach, right? Temperature is a relative thing. So when you come up with something like a temperature scale, it's hard for us to really determine temperature scales because it's relative to what we felt prior. So we go from high temperatures to a cold temperature, we feel like we're freezing. We go from a low temperature to a high temperature, we feel like we're not freezing. We feel like we're ready to go to the beach. So it's easier said than done to really come up with some sort of temperature scale. So how do we actually in practice come up with a temperature scale? Well, the way we come up with a temperature scale is we simply pick two numbers and then we build our temperature scale from those numbers. So we say this means one thing, this means something else, and then we evenly divide this into a certain number of steps, where each one of those different steps is then a degree in that particular temperature scale, and this is how we build our temperature scales. Now, having said that again, some temperature scales are better than others because if you have too fine of a temperature scale, if I went from one part of this room to another part of the room, there might be a gradient in temperature. Meaning that if I start off over here by Seth might be warm, so he's giving off a lot of heat, so it might be, I don't know, 73 degrees on this side of the room. I go to this side of the room, Ethan hasn't woken up yet, so he's colder, so it's about 72 degrees on this side of the room. Do I feel a temperature difference going from one side of the room to the other side? Even though technically this side is colder, this side is hotter, well, I, as a physical person, notice that difference from 1 degree from this side to this side? No. Unless it's like 99 degrees and then it goes to 100 degrees and then I'll definitely notice that change because I hate hot weather. But anyways, for the most part, no. So if I went from one side of the room to the other side of the room, if it changed by only 1 degree in Fahrenheit, that's not a big enough temperature scale for me to notice. So when I build temperature scales, I have to keep these things in mind. One, temperature is relative. How I feel temperature is completely relative. The other thing is if I make too fine of a scale, I won't notice a difference going from one side of the room to the other side. So when we build a temperature scale, we want to make sure that we pick our two numbers, but we pick them in such a way that the temperature scale isn't too small so we can actually have a meaningful difference in change of temperatures. Does that make sense? Good. So let's talk about some temperature scales we have used throughout history. So historically, the first temperature scale is the Fahrenheit scale. So let's talk about the Fahrenheit scale. So the Fahrenheit scale is, let's talk about some pros of the Fahrenheit scale. And then let's talk about some cons of the Fahrenheit scale. So what's a pro of the Fahrenheit scale? Well, a pro of the Fahrenheit scale is it was the first. Another pro is we use it here. And that's about it. There's basically no other pro to the Fahrenheit scale. So why is that? So what are some cons of the Fahrenheit scale? So what do you think? What are some cons of our Fahrenheit scale? Go ahead.
Having to convert it to Celsius when we do these problems.
Great, so that's one thing. The rest of the world basically uses Celsius. Celsius. I know how to spell, might be great. So the rest of the world uses it. So if I go simply across the border into Canada, now all of a sudden everybody's using Celsius and I have no idea what the hell they're talking about. So I went from 70 degrees down to 25 degrees. And I'm like, okay, I don't know what that means. Okay, so that's one con. What else? What are some other cons? What does 32 degrees mean in Fahrenheit scale? Water freezes, okay? So let's think about it. So 32 degrees Fahrenheit, water freezes. And where does water boil? 12. Water boils. Why? Why is it some random number like 32 degrees is when water freezes, and some other random number 212 degrees when water boils? Also, let's think about the temperature difference between the two. How many degrees difference between these two things? It's 180, right? Which means that the temperature scale, at least the change in degree temperature and Fahrenheit, is a very small change, as opposed to some of the other things we'll talk about. So because of these two things, this means is that the degree or temperature change in Fahrenheit is very small. So again, if I went from one side of the room to the other side of the room, changing by a single degree in Fahrenheit is not really noticeable. But the main point are these two things. Why 32 degrees? What is something that would make more sense?
0.
0, right? Why 212? What's something that would make more sense? 100, right? So that brings us actually to the Celsius scale, where the Celsius scale looks at these numbers and says, okay, if these are natural things that occur all the time, and we base temperatures off of these particular things, then why don't we make these things something more reasonable? So the overall point of the Fahrenheit scale is it is nowhere near scientific. It has no scientific basis to it. The only thing is we chose some random numbers and then built some sort of temperature scale from there. So the worst thing about the Fahrenheit scale is this is non-scientific. These numbers have zero basis on everyday events that we deal with all the time. So that brings us to the Celsius scale. So this was the second major attempt at building a temperature scale. The Celsius scale. So Celsius scale, the pro is, as we already said over here, is a con from there. Most of the world uses this. But the biggest pro is that it is actually more scientific. Again, the reason for that, as you guys already told me, is now we're going to take typical type numbers or typical events that occur all the time, which is water freezing and water boiling, and make those actually reasonable numbers. So here we set that 0 degrees Celsius is when water freezes. and then 100 degrees Celsius is when water boils. So now we've put more of a scientific meaning behind it because we've taken these things that occur in a natural state and actually based our now temperature scale off of this. So now the other nice thing is now there's only 100 degrees difference between these two as opposed to over here where there's 180 degrees difference between them. Which means that now my change in temperature in Celsius is then greater than the change in degree in Fahrenheit. So now when I change by 1 degree, going from one side of the room to the other side, it's a lot more noticeable for me to actually do that. And then the difference between these two is that the degree change in Celsius is actually equal to 9/5 degree change in Fahrenheit. Which means that 1 degree change in Celsius is almost 2 degree changes in Fahrenheit. It's actually 1.8. So this is equal to 1.8 times a degree change in Fahrenheit. Now, using these two things simultaneously, what that allows us to do then is actually get a relationship between these, which allows me now to get a transformation between the 1 degree scale to the other degree scale. And what this says then is that the temperature in Fahrenheit is then equal to 9/5 the temperature in Celsius plus then 32 degrees Fahrenheit. So here, all this is saying is that if it's 0 degrees here, 32 degrees here, then I have to add back to there. And since this is the degree change between the two, this allows me to convert now between Celsius and then Fahrenheit. Right, so this is our Celsius scale. But the important thing about a Celsius scale is even though it's more scientific than that of the Fahrenheit scale, it's not totally scientific. And the reason for that comes from something we'll talk about later, but it turns out temperature is actually a measure of kinetic energy. I'm kind of spoiling our punchline for later, but it's necessary for this conversation. So it turns out that what we measure as temperature is actually a measure of the kinetic energy of an object, which means that temperature doesn't have an infinite scale. There is an actual point where if the kinetic energy goes to 0, then the temperature of that object goes to 0 as well. This is the foundation of what's called the Kelvin scale. So what the Kelvin scale realizes is that if the object cools down enough by its kinetic energy going to 0, then it has to reach an absolute lowest bound of temperature, which is called absolute 0. When the object stops moving, its temperature has to go to 0. So what the Kelvin scale does is it takes the same idea that there's 100 steps between when water freezes and when water boils, but it also takes into account that there's a lowest bound of temperature, which is called absolute 0. And then it builds the temperature scale from there. So Kelvin then, called the Kelvin scale, is the most scientific. Because it includes absolute 0. So this is our Kelvin scale. So the Kelvin scale says is that there is a lowest bound in temperature, and that lowest temperature is when things cease to move, which then gives us our Kelvin scale. So in this case, the difference between the two then is simply 273. So my temperature in Kelvin is equal to my temperature in Celsius plus 273.15 Kelvin. This is our relationship between these two. So again, what Kelvin does is it keeps exactly the same between these two. So meaning there are 100 steps between the change in when water freezes and when water boils, which means that the change in degree of Kelvin is exactly the same as the change in degree of Celsius. But again, the difference is now it actually takes into account that there is this thing called absolute 0, which is the lowest possible temperature I can have, based on the fact that temperature is actually kinetic energy. But again, we'll talk about that later. So these are temperature scales. Now it turns out that what's known as the third law of thermodynamics absolute 0 is non-attainable. So one way that kind of ruins a little bit of Kelvin's scale, of course Kelvin didn't actually know about this, was that you can't actually reach absolute zero. And the reason for this is actually quantum mechanics. What quantum mechanics is that there's this thing called the Heisenberg uncertainty principle, which says that if I try to limit the velocity of an object, then I have to maximize its uncertainty in a position. Or if I try to completely isolate it at a particular point, I have zero idea what its momentum can actually be. So Heisenberg's uncertainty principle says that the uncertainty of the position times the uncertainty of the momentum has to be greater than or equal to what's known as h bar over 2. But anyways, all this says then is if I try to limit this, this becomes unknowable. Or if I try to limit this, this also becomes unknowable. Unlike if this was equal to 0. If it was equal to 0, then I can know both simultaneously. So basically, the reason I can't reach actually absolute 0, because if I freeze an object and I try to isolate it at a particular point, its momentum or its velocity or its kinetic energy becomes unknowable, which means that there's always this quantum wiggle, what we call quantum fluctuations. So because of that, you can never fully isolate a particle into a particular position, which means you can never fully stop it, which means you can never actually obtain absolute 0. So what's known as the third law of thermodynamics. But again, these are our temperature scales. So the way we actually create a temperature scale is we randomly pick 2 points. From those 2 points, we create a complete scale. Here, this one is just kind of nonsense, but we're used to it. This one uses 0 and 100 for when water boils and when water freezes. And then again, Kelvin uses the fact that we can reach this absolute 0, but then keeps all the best parts about the Celsius scale as well. So these are our temperature scales. In this class, this is the SI unit. So we talk about temperature, we're going to be using Kelvin. So one kind of semantic thing to point out about Kelvin is when you talk about Fahrenheit, you say degree Fahrenheit. When you talk about Celsius, you say degrees Celsius. When you talk about Kelvin, you don't say degree, you just say Kelvin. So if my temperature was 273.15, it's just 273.15 Kelvin, no degree Kelvin. Just semantic. If you say degree Kelvin, I'm not going to go test you with you. Don't worry. It's okay? So these are temperature scales. So how do we actually measure temperature then? Well, to measure temperature, we have to make thermometers. So let's talk about some thermometers. So thermometer is an object that we use to measure temperature. So this is the instrument used to measure temperature. So if we were going to build a thermometer, there has to be some sort of restrictions on the thermometer at which it is that we're going to. Meaning what types of materials we're going to use, how we're actually going to build this thing. So if I was going to design and create a thermometer, what are some reasonable restrictions on the type of materials or how I'm going to build this thermometer? So what are some reasonable restrictions? What do you think? So if I was choosing a material to create a thermometer from, what are some restrictions I should put on the thermometer? At least on the type of materials that I'm using. In the range at which I want to do it. Good. So one is that we don't want it to freeze within normal conditions. Good, Ruth. We also, number 2, don't want it to boil under normal conditions. Good, which means that, for example, we don't want to use water to create a thermometer. Because if it's freezing outside and I bring it outside, it's going to freeze and that's not going to tell me anything. If I'm trying to test the temperature of the water that I'm trying to boil, I put it in there, it's also going to boil, so that's not going to tell me anything. So I want to make sure I don't use something that's going to freeze or boil within inside of usual conditions at which I'm going to use it. What else? What are some other restrictions?
there's some other restriction.
What do you think, Sam?
Would you want it to have a low specific heat capacity so you can read the temperature quick? So it take a long time to get
Good. We could do that too. Yeah. We'll talk about specific heat later, but yes. So we want it to have a, in most cases, low specific heat. A little more specific than I was looking for, but that's fine. So, but that's a good one. That's right. So you want it to either have a low amount of material or a low specific heat so that it changes temperature quickly. Good. Because otherwise, if it has, we'll talk about this later, if it has a high specific heat or high amount of the quantity, then the amount of time it would take for it to change temperatures would be an exceptionally long time. So that's also true. Now, another question is, who you're going to use your thermometers for? So in my household, it's mostly going to be my kids. So what type of restriction should I put on the materials for my kids, for example?
Don't want it to be hazardous.
Don't want it to be hazardous, right? So we don't want the materials to be hazardous. So for example, I don't want to make my thermometer out of glass, even though we used it back in the day. But I don't want to make it out of glass, right? Because what? Put it in my kid's mouth, my kid decides to chew on it, they break through the glass, now they got a glass in their mouth, and now they're bleeding out of their mouth. Life is great. What also did we used to put inside of the thermometer? So we had a glass thermometer, and what was inside of it? Mercury, right? So if I put mercury inside of here, mercury, what's wrong with mercury? It's poisonous. So not only would they be choking on glass, but they'd also be drinking mercury, which is a both wonderful combination of badness. Okay? So I don't want it to be hazardous, right? So I want to make sure that if it broke or if it did something, it wouldn't actually kill the person that I'm trying to measure their stuff. So good. So these are reasonable restrictions that we want to put onto our thermometers. Right? We don't want them to freeze. We don't want them to boil under everyday use. We don't want them to have a high specific heat. We want to have the change in temperature happen over a quick enough time that we can actually measure it, which again goes back to something like mercury. Put that thing in your mouth, you had to wait like 10 minutes to find out what your actual temperature was. They had a pretty good high specific heat, so in that case, it took a long time for the temperature to actually be able to change. And then finally, we don't want it to be hazardous. We don't want to kill people by simply taking their temperature. So now we know what the restrictions are. Let's talk about some thermometers we've used in the past. This type of thermometer, the mercury-filled glass one, is what's known as a fixed volume thermometer. What the fixed volume thermometer does is it takes and uses the fact that under an increase or decrease in temperature, all objects increase or decrease their size. We'll talk about this in a little bit. So what this does is it uses what's known as thermal expansion. So it turns out that all objects either increase or decrease their size under changes of temperature. So what the fixed volume does is it has a certain amount of fixed volume inside. So if the temperature increases, the size of it increases, which means the mercury in this case goes up. And it does it in such a predictable way that you can measure exactly what the temperature is. If it has a temperature that goes down, in that case, temperature goes down, it then contracts itself. As it contracts itself, it does it in a reasonable way, so you can actually measure what the temperature is. Other things like this are alcohol. Do the same thing with alcohol. Similar kind of thing. We take a glass or plastic or whatever it is, put alcohol in it. Again, under changes the temperature, it increases its volume or decreases its volume. In that case, it does it again in a predictable way. So you can actually measure what the temperature is. So this is what are known as fixed volume thermometers. Other types of thermometers we use. Another one is what's known as a thermocouple. What a thermocouple does is it actually creates a circuit, and inside of that circuit, it has a capacitor which is temperature dependent. Which basically means that here's my kind of rudimentary circuit. Draw this one. So here I have a battery of some sort. So here's my battery. This is what's called a resistor. This is what's called a capacitor. So what happens in this case then is I have a capacitor where that capacitor actually has a temperature-dependent capacitance. Which means that as the temperature changes, the capacitance changes. As the capacitance changes, what that does is it changes the current running through my circuit. And as the current changes, I can then measure the difference in current, which allows me to measure the temperature. So flowing inside of here, we have current, call that guy I. So in this case, the current ends up being temperature dependent as well, because the capacitance is temperature dependent. So in this case, by measuring the difference in capacitance, i.e. measuring the difference in current, that then measures the difference in temperature, and then I can determine what temperature the object is. So what's called a thermocouple. Another one that's very similar to this is what's known as thermoresistance. So in this case, the idea is the same, except now instead of having a temperature-dependent capacitor, I now have a temperature-dependent resistor. So in this case, again, if I have a simple circuit that has a resistor inside of it, now I have a temperature-dependent resistor, which means, again, if I have current flowing through my system, my current, again, becomes temperature-dependent. So, as that guy becomes temperature-dependent, again, measuring the differences then in the temperature will then allow me to be able to measure, the differences in currents will allow me to be able to measure the differences in temperature. The last way is what's known as thermal imaging. So how does thermal imaging work? So it turns out that anything which has a temperature gives off light. Which means that you right now have a temperature, you right now are giving off light. The desk has a temperature, means it's giving off light. So anything which has a temperature gives off some sort of light. Now, it turns out that most things give off a full electromagnetic spectrum, which means that the light which is given off basically covers all possible different frequencies. So we'll talk more about this later, but basically what this is the number of photons or the probability that a particular wavelength is giving off versus the wavelength. Now what we look at is what's known as the peak frequency. So this thing has the probability curve. This portion here, where it has the maximum number of photons or the maximum probability, then corresponds to a particular wavelength, which is what's known as the peak wavelength or the peak frequency. Each one of these different peak frequencies has a particular frequency, but it's directly related to a temperature, which means that the most probable photon, or the probable number, or the highest number of photons which are given off by a particular source, corresponds then to a particular frequency, which then corresponds to a particular temperature. So anything, whether it's you, me, the desk, my dog, my foot, whatever, which all has a temperature, is giving off light all the time at a particular peak frequency, which means most of the photons which are coming off are at that particular frequency. If you measure that frequency, you can then correspond a temperature exactly with it. This is why when you buy those little guns, right, when you go into urgent care or some places, they take the gun, or if you walk into any store nowadays, they point it at your forehead and they shoot you in the head. Right? This is what they're doing. What they're doing is they're measuring the frequency which is coming off of you, which then corresponds directly to a particular temperature. This is the process. It's called thermal imaging. So what you're seeing here then is, again, different frequencies which are given off by different parts of the body, which then correspond to particular different temperatures. So here, these are the higher temperatures, things that are close to your body. Toes are further away, so then you're getting colder and colder and things like that. So this is just the way that infrared works. So night vision goggles, night vision scopes, infrared scopes, et cetera, et cetera. So all this is based off of this idea that, again, anything is giving off light. The peak frequency, which corresponds to the most likely photon which is given off, corresponds to a particular temperature. So, for example, if I was looking at something and I saw that its temperature was, or its color was yellow, like the sun, that corresponds to 6,000 degree Kelvin, or 6,000 Kelvin. Which means that the surface of the sun is actually 6,000 Kelvin. Anything there would liquefy. So this is the way that thermal imaging works. So this is another way we can actually make thermometers, is by using this. So these are what are known as thermal image. So these are different types of thermometers we can use. So again, we can use fixed volumes, which deal with thermal expansion, thermocouples, temperature-dependent capacitor, thermal resistance, temperature-dependent resistor, or again, thermal imaging, which uses light to our advantage. Okay? So good. So now we talked about thermal expansion. Let's talk more about thermal expansion. Let's start talking about thermal expansion. So how does thermal expansion work? So what thermal expansion says is that anything, any object under a change in temperature will actually change its volume or its length or its area. So changes in temperature results in changes of size of an object. Let's talk about how this works. So let's first look at what's known as linear thermal expansion, or linear expansion. So let's say I have a rod, something like that. So here's my rod, where initially at some initial temperature, this thing has an initial length. So let's say this is my initial length at some initial temperature, let's call that T0. Now, if I increase the temperature, what will happen then is that this thing will increase in length by an amount of delta L. So this will be my delta L. And what I've done is I've increased the temperature by an amount of delta T. So what thermal expansion says then is that the increased length of this object is then equal to alpha times the initial length of this object times the change in temperature. Or alpha here is the coefficient of thermal expansion. So this is the coefficient of linear thermal expansion. Now, in this case, if the change in temperature is positive, meaning the final temperature is greater than the initial temperature, that makes the change in length positive. But if the change in temperature is negative, meaning that the final temperature is less than the initial temperature, the change in length here will be negative, which means that it has actually contracted and gotten smaller. So what is alpha? So alpha is, so this side has units of meters. This side also has to have units of meters. This has units of meters. This has units of Kelvin, which means that this thing has to have units of inverse Kelvin to make sure that both sides have the same units. So alpha then has units of 1 over Kelvin or 1 over degrees Celsius. Either one of those. Remember, a change in degrees Celsius is exactly the same as a change in degree of Kelvin. Now alpha here, alpha is going to be material dependent. As I use different materials then will have a different alpha value. So this thing is material dependent. So as I change from, for example, lead to gold to tin to copper, each one of these are going to have their own different alpha values. It can actually be a little more complicated than that because it's actually not only material dependent, but it's also temperature dependent. Because if I get too high of temperatures, that starts to change the type of material, which then changes. But we're just going to say it's material dependent.
What does that say, the 1 over?
This one? K for Kelvin. This one?
Yeah.
Degrees Celsius. So this is what we call linear expansion. Now, of course, if I had an object which was, say, two-dimensional, like this, if I increase its temperature, I'm actually going to change then the entire area. So this is what we call area expansion. So let's talk about area expansion. Area expansion says is that if I took an object which has a particular area, and again, starting off at an initial temperature of T0 with an initial area of A0, and again, I increase its temperature, and the area of this object then will change. The green hash marks here are then my change in area. So So I've got a change in area, which then corresponds with this change in temperature. So what this one says then is that my change in area is then equal to twice of alpha times the initial area times the change in temperature. So that's what we call the area expansion. Finally, if I had a three-dimensional object, such as the sphere on here, in this case, I could change the entire volume of the object by changing its temperature. So in this case, let's talk about that. This is what's known as volume expansion. What volume expansion says is that if this was my initial object, with an initial volume at an initial temperature, so the initial corresponding to the initial, and again, I increase its temperature so that its volume actually increases inside the area here, then I get a change in volume corresponding again to a particular change in temperature. So what this one says then is that my change in volume is then equal to beta times the initial volume times my change in temperature. Where beta is what's known as the coefficient of volume expansion. Now, it turns out that if the object is a solid, beta is actually equal to 3 times alpha, if it's a solid. If it's not a solid, then that's not necessarily true. So okay, this is thermal expansion. So how does thermal expansion work? Well, again, if I took this guy, and I took this guy, in this case, I can actually move this guy in and out. Increase this temperature. That'll wait a little while. In this case, I'll actually call it volume expansion, meaning that overall the radius will get bigger. As the radius gets bigger, I won't be able to move it through the actual object anymore. Hope that we actually put it in. So now it doesn't fit anymore. So originally it fit, now it doesn't fit anymore. I'm not going to push too hard because I did rip this handle off before. So I'm not going to bother doing it. So in this case, I increased its volume because I increased its temperature, causing this thermal expansion. Another cool thing you can actually do is you can create a thermostat. The way a thermostat works is actually something like this, which actually has 2 different pieces of metal on each side. Each one of these 2 different pieces of metal has its own different coefficient of thermal expansion, which means that when I heat it up, it'll actually start to bend to one particular side. Then, when I cool it down, if I just let it sit here, eventually this thing will straighten back out and go back to the original shape. So this is actually the way that a thermostat works. So inside of the thermostat in this room, that one over there, is actually a piece of bimetallic strip. That's what this thing is called. Has 2 different pieces of metal. Each one has a different alpha value to it. So when I heat it up, what will happen is one of them will try to increase its length more than the other one does. So in this case, this side has a greater alpha. This side has a greater alpha than this one does. So when I heat it up, this side is trying to increase its length further than this side is trying to increase it, which means it gets bent into the side of the direction which has the smaller alpha value. So when I actually create a thermostat, what happens then is when I set my thermostat, I'm setting when this thing is either completely open or closed, depending on how my thermostat is actually working. So for example, in the summertime, what will happen is as this thing heats up, it'll bend away from the actual circuit, causing the circuit to then open. As the circuit starts to open, it then causes it to actually start running the AC, causing this thing to cool down, causing it to straighten back out, to then close the circuit again to then turn off the AC. So this is what's called a bimetallic strip. So these are nice examples of, again, thermal expansion. Now, thermal expansion is a big thing for those who want to do civil engineering. Why is that? Well, why that is because if you want to build something, when should you build? Well, you should build in a time where you have moderate temperatures. And what I mean by that is we don't want to build anything in the wintertime, because by the time it gets to the summertime, what happens? Well, the thing that I built is going to expand so much, it's going to put too much stress and strain and cause the object to break. This is what happens with sidewalks all the time. So after a while, you start seeing cracks and bulges in sidewalks because you built it at either the wrong time or it had cracks in it, and then things like water got in there, froze, made it bigger, et cetera, et cetera. You don't also want to build it in the summertime, because by the time it actually makes it to the wintertime, what'll happen in that case? Well, it'll contract too much, and as it contracts too much, it will actually pull the thing apart. So here are some examples, especially this one and this one, where thermal expansion has gone wrong. So what's happened is they created these tracks and didn't put breaks in the tracks, which allowed the track to be able to expand and contract. So as it happened is, as the temperature went up too much, it elongated too much, which puts too much strain onto it. When it puts too much strain onto it, it then breaks. So in this case, these nice big curves in the track. So what happens is when your train is coming down the track, wanting to bring something to another part of the city, for example, or some other place, like we used to do a lot here in Evansville. In this case, it runs into this, what's going to happen to your train? It's going to derail. Not good. Same thing here. So here, there were no breaks in the track. Thermal expansion caused too much, which gives you all these wonderful waves on here, which then causes derailment, which then allows you not to be able to bring the things where it is that you want to bring. This also happens on bridges. So on bridges, again, if you don't allow for these objects here, what happened then is that, well, again, if it increases temperature too much, the bridge will have too much stress and strain onto it, causing it to bulge up, which will eventually cause it to fall down. So when you build things, you have to allow for room for thermal expansion. So in roadways, especially on bridges, you see these a lot. So these are a type of thermal couple. So what this allows to do is that if the temperature increases too much, what will happen then is that these will be pushed in towards each other. But since it's broken here, there won't be enough stress and strain for this thing to actually break and take down the bridge. And then when it cools down enough, all these things are going to do is gap out a little bit more. But there's enough room for car tires to still drive over the top of it. So this is a huge problem when you're doing things like construction, designing things, especially in civil engineering, structural engineering. You have to allow room for this thing to either be able to expand or contract. If you don't do that, your system is going to break, which won't be good. So why don't we end here? We'll start off with a couple examples of thermal expansion tomorrow. So we'll do a couple examples, see how this actually works in practice. But again, these are thermal expansions. So have a beautiful rainy day, everyone, and I will see you tomorrow. Sure. Yep.
Yeah, I just don't have time. Yeah, I guess that's
Yeah, that's good.
Yes.
And then you're using
Yeah. Gotcha. Yeah. So the problem here is that you have to convert the diameter down to your meter.
hopefully I get there.
You did that, and so it worked out.
Yeah,
The only thing early
Yeah, it should be only 0.0. Right, so you converted it to millimeters instead of. So it would be 0.005 if it was 5 millimeters to a meter. Yeah, so that might just be, so yeah, it should just be 0.05.
Okay, let me try.
Okay. Hello there. Let me turn this off real quick. So we can stop recording.